Welcome back to our course on Introductory Materials Informatics. In the second part of this course, we have been dealing with a number of topics. We have been basically talking about how to set up this type of materials informatic problems. And in doing so, one of the key aspects that we had identified was proper featureization of the problem. In order to do a proper featureization of the problem, initially we discussed composition-based feature vectors, and then we started talking about the structure-based feature vectors. And in case of the structure-based feature vectors, we discussed mainly about graphs as well as molecular fingerprints. Now, in addition to graphs and molecular fingerprints, very briefly we had alluded to two-point statistics, sort of giving you a feel of how microstructure informatics can be done, how the metallurgical microstructure can be represented. Now, over the next 2 to 3 lectures, we will dive deeper into this topic and we will talk about the metallurgical microstructure, its representation, and how we can use those representation materials informatics in a little bit more detail so that you get a working idea of how to actually start using this microstructural features to set up and solve your own materials modeling problem using microstructure informatics. Now, as we get started, I just wanted to give a shout out to the book which I have mentioned over here. This is an excellent resource if you want to get into microstructure informatics. This book is called Hierarchical Materials Informatics by Surya Kalibindi. It's actually a fairly well-known book in the materials modeling community, and highly recommend anyone who is interested to learn more about this topic to start referring to this book. Now, before we dive into the representation of the microstructure, it becomes a little pertinent for us to know how we actually should start thinking about the microstructural length scale. And in order to do that, we first start by trying to appreciate the different length scales in materials and what really makes them unique. So when we talk about the length scale in materials, we can discuss that from two different perspectives. One is from the perspective of multi-scale materials modeling, and the other is from the perspective of multi-scale materials characterization. So if you think in terms of multi-scale modeling, each length scale can actually have unique feature vectors. So for example, if you are thinking in terms of very small length scales, you might be thinking in terms of the electron densities. If you want to go beyond the atomic structure and you really want to get into this molecules, you have the molecular fingerprints for one thing, but then things like bond lengths, which, as we already discussed, can be represented by edges in case of this graph representation of molecules. Those type of things also start becoming important features. As you go up the length scale, things like grain boundaries, any type of twinning that is happening, any type of crystal defects like dislocations and all, those start becoming important. And then the grain size of the material becomes important. And then those are the type of features that we start thinking about when we talk about doing some sort of microstructure informatics. Now, one thing I cannot stress enough, if you look at the features at one length scale, these features do not necessarily translate to a different length scale. So for example, if you're looking at the electronic structure calculations, this ideas of electron densities and all might be excellent way of thinking about the problem. But when you are thinking about this from at a microstructure length scale, you will actually have to come up with different features and not focus so much on things like electron density and so on. So whatever type of modeling method you use in one length scale, those are characterized by one set of features. They do not necessarily translate to another length scale. And therefore, when we talk about different length scale, we have to think differently in each of the case. Similarly, when you are thinking in terms of materials characterization at multiple length scales, you have to appreciate that each length scale has a unique set of characterization methods. So for example, if you are thinking in terms of imaging domain structures, you might be using something like magnetic force microscopes, right? However, if you want to identify the oxidation states in a material, you might actually want to go ahead and use X-ray photoelectron spectroscopy. If you want to understand the crystal defects, you have to use a proper tool. For instance, people use a transmission electron microscope when we're looking at dislocations. People use the TEM even when they're looking a little bit in depth into the structure of grain boundaries. people can use scanning electron microscope for looking at a variety of microstructural features. So basically, a single technique does not suffice across all of these length scales. So to drive home this point a little bit better, let us actually take an example with something like a composite material. So if you look at a composite material at the microscopic scale, now you start looking into this fiber matrix interface, things like thermal expansion and all, that becomes important. Now, what you really begin to appreciate is when you are trying to subdivide this composite into the fiber and the matrix. We inherently assume that these fibers in themselves are going to be homogeneous. The matrix in themselves are going to be homogeneous. And then it is the interface of the fiber and matrix where all the action and the fun happens. Now, instead of looking at the microscopic length scale, if we start looking at mesoscale, we can think in terms of something called a RVE, or a representative volume element. So this representative volume elements is essentially going to be a collection of smaller units. And one of the things you have got to keep in mind is when you are looking at the properties of these RVEs, you assume that things are homogeneous within the RVE. Moving on from the mesoscale, one could go to the macro scale. And here what we do is we assume that there is a continuum, and you kind of think that your material overall is homogeneous at that length scale. So what I really want to emphasize here is that computationally we tend to think of length scales as the length over which the properties are homogeneous. Anytime as you are reducing the size of the area that you are looking, and you start seeing that the properties are becoming inhomogeneous, whether you are reducing, whether you are going up the length scale, doesn't matter. But as you are changing the system size and you see that your properties are no longer homogeneous, that is where you understand that you are having a change in the length scale. So that is how we will think of it computationally. When you come to the experimental side of things, basically when you are looking at the multi-scale characterization of materials, ideally this concept of length scale simply deals with how well you can resolve the features at different levels. Okay, so you might be able to resolve the electronic features at very small scales, but when you look at a larger region of a material, it's very difficult to resolve the electronic features, and you start thinking in terms of a microscopic feature, or you might actually think in terms of something even larger if you're going from a microscopic length scale to a macroscopic type of length scale. Now, coming specifically to the microstructure of the material, the way we want to go about representing this is to come up with some sort of a mathematical function which will start describing the microstructure. And then if the microstructure is homogeneous enough, maybe there is going to be some amount of periodicity in this mathematical function. And once you start dealing with periodic functions, there are very well established mathematical techniques that can be used. So that is going to be our overall game plan when we dive into microstructure informatics. Now, as we get started, I want to introduce a couple of concepts. One is the concept of a local state, and then the other is the concept of a local state space. So this concepts of local states and local state spaces, these are direct implications of homogeneity of select properties when you are looking at a given length scale. So from a philosophical standpoint, one can say that if a smaller length scale exists, then there must be some sort of local states in the material. If a smaller length scale exists, it means that there are certain properties which in those small domains are actually different from each other. That's how you are able to distinguish between those domains. That's where your concept of the length scale is coming in. And therefore, it follows that if you do have smaller length scales, then there has to be local states within your material. Now, the property might be homogeneous at a given length scale, but the existence of the smaller length scales, just as we discussed, also implies the inherent inhomogeneity also being there in the material. So essentially what you start appreciating is something that we have been talking all along in the last few lectures, that materials are inherently hierarchical in nature, and there exists some sort of a structure-property relationship at every length scale that we can think of for that particular material. So what we are now going to do is we will define local states. So this function h is a function of let us say rho and ci, and this is something which defines a local state. Now rho is what we would call a phase identifier. So that would be a label which is associated with different phases in a material. So something like gamma iron or alpha iron, those are different phases. So you can use gamma iron, alpha iron as the phase identifier, which we are going to denote by rho. The other part is the composition. So once you have the phase, once you have an idea of the atomic arrangement, because each phase would have a unique crystal structure, or maybe they would be amorphous, whatever it is, there is a related atomic arrangement associated with the phase. In addition to that atomic arrangement, the other information that is encoded within the phase is what the composition of this phase is. So that composition we are denoting by Ci, where I is basically the ith species, Ci is the composition of the ith species. Now, if you have got a bunch of local states together and you have a set formed out of a bunch of local states, then we have got something which we call a local state space. And so this local state space, that we are going to denote by this letter capital H, whereas only the local state we are denoting with the letter small h. So the distribution of the function that defines the local state space as a function of the length is really what defines the metallurgical microstructure. When we look at materials engineering problems, one of the most common type of microstructures we would encounter would be the polycrystalline microstructures. Now, this is not to say that single crystals do not have their applications. They do have a lot of applications. They also happen to be relatively easier to deal with mathematically as compared to the polycrystalline materials. So let's actually get into the polycrystalline materials and look at what one would think of as a relatively hard problem. So for our purpose, when we are trying to define this type of polycrystalline microstructures, we need to define the coordinate system which is associated with this type of microstructure. So when we talk about the coordinate system, we will have one set of coordinate system which is associated with our overall sample. So there would be a x, y, and a z direction for our sample itself. And then we will have a second coordinate system, or rather a series of the second coordinate systems, which are associated with the individual grains. So essentially, when we are looking at this type of polycrystalline microstructures, we now have come up with two different Cartesian reference frames, one which is associated with the frame of reference for the sample, the other which is associated with the frame of reference for the crystals themselves or the grains themselves. So I'm just going to show over here. Now, if you look at this black system of coordinates and the green system of coordinates, you will see that the one is rotated a little bit compared to the other, but they are actually two different systems of coordinates. So let us try and think about it. So supposing we start with a sample frame of reference, and let us say that we describe this using three unit vectors, E1, E2, and E3. And then let us say for a particular crystal or a particular grain, we have this second frame of reference, and here the unit vectors are given by E1 prime, E2 prime, and E3 prime. Now, what is really happening over here is we are rotating the first frame of reference by an angle theta in order to generate this second frame of reference. All right. You can understand that the E3 unit vector is pointing in the same direction for the grains as well as the sample over here. So if I rotate one of the system frames of reference by an angle theta, I can start generating the second frame of reference. So what really happens when I'm rotating it? This rotation can be described by using a rotation matrix. So this rotation matrix is given by this. Now essentially what is really happening is this angle theta is really the one which starts describing the rotation matrix, and essentially the rotation matrix is simply consisting of the direction signs and the direction cosines. So you have this type of relation that the rotation matrix is given by ej prime dot ej. So it's just a dot product. And then the components of the transformation matrix is simply basically going to be the direction cosines of your basis vector. Okay. Now, one more concept we need to define at this stage is this formalism that was developed by Leonhard Euler. And according to Euler's formalism, one can describe the coordinate system uniquely by using a sequence of 3 rotations, which have to be taken about specific directions. So this rotations, the amount by which these rotations are done, the angular rotations, these are defined by the Euler angles, and each Euler angle is associated with each of the 3 directions. So you've got 3 Euler angles and they're associated with 3 of the directions, and each of the Euler angle is basically a rotation about one of those directions. So let us actually see how this thing is going to work out. So let's say I have this initial frame of reference, and now I am going to do a rotation, let us say by an angle phi 1 over here. So as I do a rotation by an angle phi 1, now this E1 unit vector is going to come to this position. So let's call that as E1 prime. And similarly, the E2 unit vector also gets rotated and it comes over here. Let's simply call that E1 prime. Okay. So now, if we look at the next rotation, the next rotation can occur when we rotate this new frame of reference. So this old frame of reference is given by the blue ones. The new frame of reference, which we get by the first of these rotations, is over here, E1 prime and E2 prime. And now what we are doing is, having done the initial rotation around E3 by phi 1, we now do the second rotation around E1 prime by an angle phi. So as I am doing the second rotation by this angle E1 prime, what happens is, since I am rotating about E1 prime, this axis itself is going to remain unchanged, but then the other axis starts to change. And so this E3 now comes to what I would call as E3C, and then this E2 is again going to come to what I would call E2 double prime. I'm sorry, this E2 prime goes to E2 double prime. And then essentially what you can see is this E2 prime is getting rotated by the same angle phi, which is the angle that I am rotating around E1 prime. So in Euler's formalism, you can think of this as the first rotation. You can think of this one as the second rotation. Now let us come to the third rotation. So again, we start with our original coordinate system. This original coordinate system, after the 2 rotations, had come to where I would have this dash lines over here. So this dash line corresponds to E1 prime. This dash line corresponds to E2 double prime. Now we have rotated about the E3 axis, then we rotated about the E1 axis. Now what we are going to do is, we will go ahead and rotate about the E3 axis. And each time when we are doing the rotation, we are not doing the rotation about the original axis, but we are doing the rotation about the transformed axis. The first rotation is always about the original axis. That rotation is now going to transform the coordinate system. All of the subsequent rotations are about this transformed axis. So when we rotate about E3C, let us say by an angle phi 2, then what happens is this E1 prime is going to get transformed to a new location. Let us call this EC1, and similarly E2 double prime is going to get transformed to a new location called EC2. So associated with all of these rotations, you can start writing down the transformation matrix. So the first transformation matrix is a rotation along this E3. So let me call this as QKL, and this thing will be given by cosine of phi 1, sine of phi 1, 0, and then you have minus psi phi 1, cosine of phi 1, and then you have a 0, and then you have 0, 0, and 1. Okay. The second rotation, for that the associated transformation matrix, if this was KL, then this is going to be JK, because the rotation is around E1 prime. So the matrix in this case is going to be given, the stop row would be 1, 0, 0. So as you can see here, the rotation around E3, so I've got 1 in this position. In this case, the rotation is around E1 prime, so the 1 comes over here, and therefore the other components of this matrix is going to be cosine of 0, cosine of xi, sine of psi, and then 0 minus sine of phi, cosine of phi. And similarly, one can write down the third transformation matrix as well using the same logic.